Good day, good day. I also wanted to ask if you've eaten, if those calories have already reached your brain, because our topic is about security. Yes, about cybersecurity. I'll tell you right away, there's a lot of content. I will try to condense it, tell it more interestingly in some parts, condense it in others, but there's a lot of it. There will be slides. In the slides, there are a lot of links. This is homework. Yes, for those interested in cybersecurity, know that this is just the beginning, not the end. Okay? Our topic today is the protection of robotic and autonomous systems. How to build protection from an architectural perspective, what to pay attention to. My name is Anastasiia. My name is Anastasiia. I am the head of security engineering at Cossack Labs. Cossack Labs is a British-Ukrainian company. It is a company that deals exclusively with cybersecurity. We say that we are a full security solutions provider. The company is already 10 years old. Hooray! We weren't hit by a missile. And we have our own cybersecurity software. In fact, it involves data protection, encryption, part of it is open source, and the proprietary part is free. We also work a lot on cutting-edge technologies, and we conduct audits and assessments. This specialization is exclusively cybersecurity and everything related to it. Before the full-scale operations, we were engaged in regular commercial projects with companies from fintech, large industrial complexes, and simply large applications with millions of users. Then AI, ML, and the protection of ML model data began. But with the start of the full-scale operations, we have been very actively supporting the security and defense forces and collaborating extensively with various structures, units, and manufacturers. And a lot of the content in today's presentation is heavily censored because no know-how, no specific things that are currently being used can be disclosed since they are in use right now. If you are interested in specific details, please find me on LinkedIn, then find me on Signal, and I will gladly tell and show you, but not to a wide audience. What will we talk about today? About the architecture of robotic systems, about security goals and threats, about the security components of systems, and of course, some cases, some examples. Let's begin. You might recognize some of this. Yes. When we talk about robotic and autonomous systems, we can imagine different things, very different things. Again, censorship, I'm not saying anything about that. We will pretend that we are talking about IoT, industrial IoT, yes, about very specialized devices, not consumer-level devices, but specialized devices and systems used in various operations. For example, for exploration, for control. Fields, agriculture. For missions like demining, for logistics, very humanitarian. As you know, with such devices and systems, there is a bit of a difference between these and regular consumer IT, sensors, lights. Yes, a lot of what I will be talking about today might seem a bit paranoid, because these security controls are for specialized systems with high risk, with high levels of security necessity. So if you hear something and think, oh damn, well that's real, yes indeed, for some systems, especially for regular consumer systems, this might be overkill. For specialized ones, this is the basic level, it's not enough. And so about the architecture, there are very different approaches to building your robotic system. And when I say robotic system, we mean several components, many devices. Here on my slides, I will be using such a typical architecture. We have a device, board, apparatus. It can float, fly over water, underwater, drive. Yes, the device can simply lie statically somewhere in the field, tied to a tree. Devices can be more intelligent, where there is a real but trimmed operating system, where there are several good processors, sometimes indeed several. Or devices can be quite simple, where there are rather primitive processors where the computational resources are reduced. These are all devices. We love them all very much. But the level of security, of course, what we can afford in terms of security will very much depend on the hardware present on these devices. But in general, we are talking about devices having SOC, sensors, output devices, and some cryptographic module. Yes, a TPM or something similar. There is data storage, a flash drive, or memory. And there is firmware, software, meaning applications that are on the device. Then this device communicates in some way. Let's not limit ourselves. We will also talk about radio communication. This could be radio communication with a base station, which could be either another specialized device or a radio remote control, for example. It could be communication over the internet, again with a base station, which could be an operator's laptop, for example. Or it could be direct communication of the device with what we will call the backend, or the centralized part. I call it core infrastructure. Core infrastructure is something that usually can be either a cloud system or a system on its own on-premises servers. But the idea is that the devices collect some information, they gather something, they analyze something, and either they make decisions, in which case they are smart devices, or they send part or all of the information to centralized systems. And then the centralized system processes it and returns commands to the device, for example. This is also a typical pattern. Centralized systems. What are their characteristics? They can receive telemetry from the device, images, video streams. You can build security systems there. There is some kind of transport there. For example, if we talk about the internet with VPN, we can build data analysis and anomaly detection there to return something to the device if something goes wrong. And of course, if we are talking about many devices, there is usually a fleet manager on the centralized system that allows you to manage these devices in one way or another. We are now agreeing on the terminology with you about what we will actually be discussing. From the point of view of topology, topologies can also be very, very diverse. I have highlighted 3 quite popular ones here. For example, a device communicates with a base station, the base station communicates with the backend, or many devices communicate with one or data base station, which communicates with the backend, or a mix. Some devices go directly to the backend, some devices go to the base station, or even mesh topologies, where devices communicate with devices, devices to devices. And there, if you're lucky, someone goes. So we are now saying that from the perspective of architecture and topology, robotic and autonomous systems are very diverse, incredibly diverse. And that's why there is a lot of content in this presentation. Because just as the systems are diverse, so are the ways to protect them. Do you understand what I'm saying now? Sounds good? Yes, raise your hand if everything is as expected so far. Okay, good. And then please raise your hand if you already have experience either as a developer or as an architect, as a manufacturer with robotic systems, or as a user of autonomous systems. Well, yes, vacuum cleaners. Okay, let's call them vacuum cleaners. You know, a smart vacuum cleaner. You have a 2-story house, 2 independent vacuum cleaners, a base station, and an anomaly detector. Did we suddenly run over the cat? Good example. Thank you. Otherwise, I keep saying agrodrones, vacuum cleaners. Okay, let's move on. What are we protecting? Usually, devices have some IP, intellectual property. Yes, it can obviously be the device itself. It can be the firmware on the device. It can be specific data that we record on this device. These can be ML models. Currently, a very popular approach is processing ML models on edge devices. That is, instead of having one huge ML in the cloud, we create small optimized ML models, and our devices execute them, obtain results, and make certain decisions. What's the point? The point is that usually such ML models are highly specialized, they are very well trained, and in many cases they are updated very quickly. The company that trains these models wants to protect them. Yes, it's part of the IP, and of course we protect it as well. Next, devices. should be protected to ensure that no one can break into the radio channel or internet channel and simply hijack our device. And there are various possibilities there. The worst case is probably to turn around and send our vacuum cleaner back, or to the place it came from. Well, it left like that. Number 3, the operator's location. In fact, the operator's location from a security standpoint is what distinguishes our world now from the very typical commercial algorithms and protocols for working with robotic devices. Because in the commercial world, the operator's location is not sensitive. It was not protected. There are many aviation protocols where the operator's location is obvious. We understand that the operator's location is often secret because the device is just a device, but a trained person is much more important. Therefore, in the modern world, we in Ukraine have to modify some things and reinvent them, adopt NATO standards and so on, precisely because ordinary commercial standards simply do not fit. And lastly, it's about the resilience of the system itself. This means that there is physical access to the devices. We understand that it's not a question of whether there will be access. There definitely will be. The question is when it will happen. And in fact, one of the design requirements from a security perspective for the system is to build it in such a way that if someone reverses our device, then they cannot learn about our centralized system and gain access to other devices. Unfortunately, such cases have already occurred even in Ukraine, where the loss of one board, the reverse engineering of this board leads to centralized infrastructure and control over other boards. What does the modern world tell us? That the risks and threats to such systems, there is a very rich list here. I didn't finish rewriting them all. Here we will talk from operational risks, organizational risks, to software, hardware, supply chain, and many more. If we analyze each stage of the data flow, each component, we can list many risks for each of them from a security perspective. Of course, the first question arises how to choose. And that depends on the goals of our device and what exactly we want to protect. What does the internet tell us? OWASP top 10. Have you heard about the OWASP top 10? Well, say yes, let's shake hands. Okay. But have you heard about the OWASP top 10 for the web? Because usually when people mention the OWASP top 10, they mean web applications. OWASP is a huge community, and their top 10 is not just for the web. There is a top 10 for mobile and a top 10 for IoT. Well, the top 10 is the 10 most critical risks for that particular platform or ecosystem. According to the OWASP community, yes, purely about security. OWASP top 10. Here, I don't think you'll be reading this. Look, this is the year 2018, 6 years ago. Yes, of course, some risks haven't changed, some threats, but overall we can consider this a bit outdated. I just wanted to show that this exists. If the question arises, how do I build security for robotic devices? Please. The first thing you can start with is to read OWASP, because smart people have already thought about this. Next, smart people have thought about this very thoroughly. Therefore, OWASP also has another repository called the OWASP, ISTJ, IoT Security Testing Guide. This is essentially a guide on how and what to pay attention to. Here too, you see, I don't want you to read, I just want to impress you with the number of squares. This is about each component and specific threats at this stage, or the system component. I highly recommend it. The link is below. You will have the slides. As I said, the homework will be quite thorough. What is all this leading to? To the fact that there is a starting point. Of course, if you have already started with security and want to dive deeper, OWASP is just the tip of the iceberg. You need to read the primary source. The primary source is NIST. In NIST, you open any standard, there are 400 pages. Go ahead. I recommend, if we are talking about the security of robotic and autonomous systems, I recommend these 3. The first 2 are NIST, Special Publication 800-2 These are specific guidelines for manufacturers of IoT devices. There, in principle, it's about smart bulbs, meaning it's at the consumer level. But it's still interesting. If, God forbid, you are involved or know someone who is involved in the production of robotic devices, at least take a look at what's there. They highlight very interesting issues that we might not consider in the pool of work. Below is NIST. 882, these are guidelines for adults. This is a guide for OT, operational technology. Yes, for if you are a large company and you have not only IT but also OT, then how do you build a process? How do you monitor security? Here we are no longer talking about a specific device or system of devices, but about the company that produces it. Very interesting. 400 pages, but very interesting. Of course, if you want something shorter, then this is the last link. This is directly a handbook. Again, for device manufacturers. All the links will be provided. I highly recommend it. Yes, that's a photo, good. Let's move on. So this is mine. This is all an introduction. Architectures are complex, with many risks and threats. What to do? This is the minimum. This is the minimum of what to do. As we have complex architectures, we analyze risks, we analyze threats, and choose the most critical ones. Usually the most critical will be payload protection, communication protection, and protection against reverse engineering. We start building protection, methods against them. I listed them. Seriously, these are not all. What do I want to draw attention to here? To zero trust. Have you heard about zero trust? Yes. Zero trust is a concept from a security perspective that we do not trust. In short, it's about authentication. We do not trust either devices or users. We authenticate everyone. What does this mean for us in terms of robotic devices? If a human user connects to a device, we authenticate them. Yes, all devices with login password, they're private, these private keys. Furthermore, if a device connects to the network, we authenticate it. All devices have, again, identification and authentication. This can be a VPN. It can be VPN, private keys, certificates. It can be key exchange. If we are talking about cryptographic protocols, like in TLS, exchange keys, interaction started. But without authentication, we do not trust the device. Why is this important? Because unlike the world of web applications, where we think, oh, an attacker will break our web view, in robotic devices face slightly different threats. Yes, an attacker can break our device, and we need to track this. And what if an attacker adds a device to our network? Such attacks are called evil twin. Yes, a malicious twin. What does this mean? That your network, your system must not only identify and authenticate its own, and distinguish if behavior changes, and be able to identify outsiders who have just joined and want to communicate with the network and obtain some information. Also, unfortunately, there were such cases. During the hot summer of 22 to 23 with some manufacturers, what else do they pay attention to? I think you've heard a lot about supply chain security. And this is an endless topic. It's a problem of why we trust, which vendors we trust, starting from hardware components, ending with, if we talk about hardware, the assembly line itself. The way you integrate these components into a device. And what if someone places RTech there? And what if someone places a GPS tracker here? That is the physical security of the device. It starts with how these devices are assembled in principle, and then a level higher, to the level of the operating system. Why do we trust? To an even higher level, to the software level. Which library components do we use? Supply chain security is really a very paranoid rabbit hole, which is very easy to fall into and very difficult to get out of. Some manufacturers say, what can we do? We have to use it already. We accept the risk as it is. This is a security concept called risk accepted. We accept the risks that there really can be incidents, problems like Chinese software. Some manufacturers try to find a golden mean. For example, if you know, there are already tools on GitHub for tracking Russians. Not like that. Software written by Russians, open source libraries. You can simply do typical dependency management and not add a component that doesn't seem reliable enough. Of course, some manufacturers say, we want to minimize such risks altogether, everything our own. We will very rarely use someone else's. We will write our own software, our own libraries, or take a copy from them and maintain it. We understand that here we are exchanging time for maintenance. We don't move as quickly, but we have more control. We need more people. They must, and so on and so on. We will now focus on some of these squares. Let's start with provisioning. One of the thoughts, Kato, I would like you to leave this room with, is that people are not needed. When we talk about provisioning in general, and especially robotic devices, people are very bad at executing the same commands over and over again. Imagine you don't have 5 devices. Imagine you have 50. God forbid, 500. For each of them, you need to assemble them there. You need to install the firmware on each of them, check them, set encryption keys, perform self-checks. These are complex processes. Recommendation number 1, infrastructure as code. We automate as much as possible. They codify the code separately, and the keys and configuration separately. And a single script that applies all of this. Similarly, tests, health check tests, apply the configuration and verify. What is interesting about robotic devices from a security perspective that is not present in web development? You can mess up so badly that the device just becomes a brick, and that's it. Therefore, testing of tests. What else is interesting here? The problem of identifying the provisioning process sounds very simple. How to identify your device? No, it's not about 64-byte IDs. This problem is also much deeper. How to identify your device and all its components? How to then ensure that it's not someone malicious who disassembled 3 devices, assembled a Frankenstein device, and is now going into the network? How to distinguish this malicious twin? Yes, how to distinguish by the identifier whether it's ours or not. When the process of building robotic devices becomes industrial, versions appear. You get a device version 1, firmware version 2.7, and so on and so forth. Identification, but the problem of identification is how to gather all this information to understand exactly what kind of device it is, when it was made, whether it is ours or not. What trust artifacts it should have, what cryptographic keys, for example, should be tied to this device. I won't talk more about the problem of identification. In the end there, I will show one of the examples of its possible partial solution. I also won't talk much about cryptography. You probably already know this. If we have a device and it has a cryptographic module, it would be very good if it does. If it doesn't have one, it needs to be added. And what advantages does this provide? We can encrypt data specifically for this device. We can perform cryptographic manipulations on the device. We can, for example, sign firmware for the device or even sign and encrypt it for the device, Nishat, and be confident that only the one who has this key will be able to decrypt and install it. A piece of code where something primitive is happening here. We open the Lux container, gather the key, and organize the storage into folders. But this is a piece from our core provisioning of our device or our devices. We also have some software, hardware solutions for certain problems. And much of what I'm talking about is simply the experience of us bricking them, messing up, and similarly not assessing certain risks. But the main idea, no people, no problems. Sorry for the noise, or maybe not like that. When there are people, problems always come with them. Therefore, the more automated the processes of deployment, provisioning, testing, and support communication are, the better, simpler, and easier life becomes. Let's move on. Not tired? No, it's fine. Deeper? Or is it enough? Or just on the surface? because there's more, as there will be a couple of hardcore slides. Okay? Let's move on. Hardening of the operating system. Who is familiar with what operating system hardening is? Raise your hands. Yes, 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 yes. Who likes this process? Oh, yes. Okay, okay. For those who are not familiar, because only a few people raised their hands, operating system hardening is when, let's say, first of all, it's a smart device. It has an operating system which is already good. There are different types of operating systems. There's blah, blah. If we are talking about something Linux-like, then operating system hardening means removing everything unnecessary, removing modules you don't use, packages you won't install, applications, files, but removing as much as possible. Next, update the operating system. We, for example, recommend using LTS, because another common issue with robotic devices is that once configured, it drives off, flies away, or sails away. When you will update it next time, no one knows. So, God forbid, if there is some kind of auto-update, it won't be good. Link and remember the operating system on the latest tested LTS version that you are confident in. In most cases, you might not need the very latest version, the latest stable one, because you will have to live with it for a very long time. Because the update cycle for robotic devices can be 1, 3, 5, or even 10 years. And some devices are installed and not updated at all. They just work until they stop. Next, another interesting thing you can do in terms of hardening is to disable root, divide users into different groups, and disable certain permissions for some applications. Of course, we are talking about using LUKS encryption and secure boot. Who, the last point, has the time and inspiration to look into Linux? I know very few manufacturers who have reached this point. What else is interesting here? In general, the update process, not even of the operating system, but of the firmware, is very interesting because the device, if there is automatic updating, needs to download this data somewhere, verify its integrity. And God forbid it gets updated by attackers to a firmware they need. And verify the integrity, decrypt if necessary, try to apply this system, this firmware, this version to a separate partition. Switch, yes, yes, no, no, be able to switch back. It's very complicated. Over-the-air updates of this type are very complex. They need to be tested, and tested again. If it gets stuck in the middle, it's a brick. If the internet goes out and you needed it because there are some synchronous APIs, back and forth, it's a brick, right? What can help with hardening the operating system? As I said, there are no problems if there is no operating system. Below is a link to Linus, which is one of the popular utilities. It's like an auditor. You run it on your Linux, and it audits, conducts an audit of the security settings in your operating system. It's a cool thing, of course. Let's put it this way. Of course, these tips are very basic, because when you build your device, you know what's there, what you need, which modules are needed, not needed, which ports are needed, not needed. Linux just helps with this. And the second utility is awesome security hardening. It's a source of inspiration. If you've already done everything and don't know what else to do, you can read there. Let's move on to cryptography. My favorite, how we store and protect data. I've divided this into 2 slides. Let's have a brief preview. This will be about the payload. You see there's an arrow from the the infrastructure to the device. That means we are sending some data to the device, some payload. And my next slide will be about telemetry security. This is when the device collects something, some telemetry, and sends it back to the centralized storage. From a security standpoint, both need to be protected, but they can be protected differently. When we talk about payload, let me remind you, we are referring to specific data, files, maps that are needed on the device, which need to be uploaded there. Sometimes this is done once during the provisioning process, and sometimes they need to be updated. These could be ML models, as we mentioned, yes, something that the device needs, which it will receive. It could even be commands. that we send from our centralized system to the device for it to perform certain actions. Before sending, as we already mentioned, the device needs to be authenticated. Next, we recommend sending the data encrypted, ideally encrypted separately for each device. Why is that? Because on the device we have a TPM, there are cryptographic keys. We have built a key hierarchy there. Do you remember what was there at the provisioning stage? Didn't build it? Sorry. But if we did build it, then we can encrypt the data for the device. That is, even if we have the same model, 10 devices, it will be encrypted with 10 different keys. Why is this important? Because they might intercept and decrypt it. It's more difficult to decrypt if each device has its own slightly unique version, at least encrypted with a unique key for that device. What else is interesting here? Because the device usually receives this data, it decrypts it, checks its integrity, decrypts it again, and stores it. Of course, here you see the step re-encrypt. We call this encryption for transport and encryption for storage. Received, re-encrypted, and re-encryption can already be done with the device's keys, which the backend does not know. Thus, if the device is lost, these keys are tied to this device, right? Good luck decrypting. Of course, I am not giving recommendations on which specific encryption to use here. It greatly depends on what you are building and how basic our device is, as well as what cryptography is available on it. Because in cryptography, there is a separate category called lightweight cryptography. Well, lightweight cryptography is a kind of primitive cryptography for basic devices, but it retains its properties. Here, from what we often use, author and recommend, is HPKE. This is hybrid public key encryption. It's quite a modern scheme of hybrid encryption, both symmetric and asymmetric. I won't go into details, as this lecture is not about cryptography. I recommend reading the sources. There are links to the RFC. Or ask me later, and I'll explain. What's the point? The point is that it allows you to create such an asynchronous message in one packet and decrypt the data uniquely for a specific recipient, that is, for a specific device. Telemetry. The process is reversed. The device collects telemetry. It collects, and stores it for some time. What? That's right, it encrypts when storing. Then, when it is ready to send to a centralized device, it decrypts from local storage, re-encrypts for sending, and sends it. What's interesting about telemetry? We are not always concerned with privacy in telemetry. Sometimes, but we are always concerned with authenticity. What does that mean? For example, the device's coordinates or video stream might be public in some cases. Yes, privacy is sometimes important, sometimes not. But authenticity, ensuring that we received these coordinates from this specific device and that no one altered them in the process, is what interests us the most. Why? Because you might think the device is sending telemetry, and you might think it's already over Moscow. Send it a command to do something, but it's actually over. Yahotin. Well, oops. Yes, that's why authenticity is super important when sending telemetry back. As I said, sometimes it's more important than confidentiality. And why do I emphasize this? Why? Because sometimes we want to make the telemetry sending protocols more optimized. Every byte is important to us. And encryption may not always be a good option, but authenticity verification, signing, and integrity checking might be sufficient. That's it. What do we recommend here? It's to use AEAD if encryption is possible. This is authenticating encryption with additional data. Well, you know, it's like ISGCM, for example, that kind of thing. But again, I don't want to give specific recommendations on ciphers, because each device may or may not have a crypto module that can or cannot do this. Yes, I see you're gradually getting overwhelmed, so here's a nice picture. Do you know what this is in the picture? Shout it out. This is a dramatic pause to drink some water. This is called a tamper evident sticker. Such a trendy word, tamper evident, meaning that we have evidence. Evidence, thank you, that we have evidence that the device was attempted to be disassembled and modified. You have definitely seen such stickers. They are very often holographic. They have two parts. How is this done? For example, here is a device. We don't want it to be disassembled. We stick the stickers here. And then, when it is disassembled, this sticker tears a bit and leaves one part on one side and the other on the other side. Reattaching it as neatly as it was is very difficult, almost impossible. Why am I talking about this? This is a very cheap way of physical tamper evidence, but it is not tamper-proof. There is a difference. It's just proof that someone tried to disassemble it, but it doesn't protect in any way. Such a sticker does not prevent attempts to disassemble. So, why this slide? It's about protection against reverse engineering. Well, listen, some people think that if we just stick on some stickers, we'll be all set. Of course. No. About reverse engineering. We have already agreed that the device will eventually fall into the hands of a malicious actor. The question is when. Our task as architects of robotic and autonomous systems is to consider that this will happen while we are still designing the architecture. From a security perspective, reverse engineering is a cat and mouse game. We want our devices to have so many different protection methods that reverse engineers simply get tired and stop, or that they lack the skills. But we know that the issue of skills is a matter of time, so they get tired and stop. How? How is reverse protection built? Everything you can think of, this is the field where you can let your imagination run wild. Sometimes engineers really enjoy working on reverse protection without dealing with cryptography, identification, or firmware protection. A bad option. We recommend doing the opposite, first implementing proactive security controls, and then reactive security controls. What to pay attention to if there is code obfuscation, can be very annoying. It's simply trivial, even built into the programming language or their third-party packages for this programming language. If possible, you can implement debug detection in the code. That is, you can try to find out directly from the code whether we are being debugged or not. If we are being debugged, we raise a flag, delete something. Next, honeypots. Honey tokens? Do you know what honeypots are? Yes, good. Who doesn't know what honeypots are? Okay. Honeypots of honey, they are decoys. We lure the attackers so that instead of reversing something really important, they reverse our decoy. Honeypots come in many different forms, and they have various names. Honeypots, honey tokens, poison records, canary tokens. Slightly different concepts, but one principle. How can this happen? If it's code, we add fake files, fake methods to the code. We can simply, if the device allows us, record a lot of fake data onto a flash drive. If you have this much main firmware, add this much more, let them figure out what is valid and what is not. Of course, if you do this, very primitively, a deemed good reverse engineer will find which methods are called and which are not. It can be made more complex. But here, why I say it's very fun is because you can spend a lot of time complicating such systems. Next. Honeypots can be, for example, a fake SSH. You move SSH from the default port and place a fake SSH on the default port. For example, a cool utility down there is SSH Sesam, well, like SSH Isam. It makes the attacker think they have connected to a real SSH, but in fact it says, wait, and it just wastes time, the person's time. Then some errors, connection error, let's start over. So in short, what else is important for reverse engineering? Delete data as soon as we see not anything that attempts to reverse. Remember, we talked about the pilot and important data, telemetry, important data, ML models, files, videos, important data. If you see that the device starts reversing, someone starts reversing, you delete the data. Why is encryption such an awesome topic here? Because if you store data encrypted, even if there are many gigabytes, you delete the encryption key. Small, simple, very fast, and good luck in decrypting gigabytes of encrypted data. What else is interesting here? Often in reverse engineering, it's said that when devices are made industrially really complex, they have several processors, several of these systems on a chip, and there are, for example, the main smart ones, and then there are these small pure beacons. If the main device has deleted all the data, then so that the person, manufacturer or user can still find the device, the small beacon still, for example, sends information about itself and sends health checks. This is also very important to consider at the stage of device creation. Okay, that's it. I'm finishing. The last point here is very interesting. Some do it, some don't. To be able to mark a device as untrusted in your fleet manager, for example, if you lost it, and if there is a connection with the device, trigger a command to delete everything, or at least mark it. See in the fleet manager that something is wrong with some devices, and there are some anomalies like they are teleporting in GPS, for example. That's it. I'm finishing up. I don't have time anymore, so I will tell these examples very quickly in a minute. Well, I'll try. Look, I've told you a lot today, but again, these are just the highlights, really just the highlights, because the architecture of robotic and autonomous systems is vast. From a security perspective, we are also building a large protection system. If you're interested in a slightly more structured approach, we have a lot of materials on the website, censored, pre-censored, but technical enough to read the concepts. For example, here we are working with Ukrenergo, and one of our solutions is a hardware-software complex for telemetry protection. Keywords, metamanig, SCADA, IKIS. If the word SCADA doesn't fill you with awe and fear, then it's a pity, because it's very interesting. If you're interested in more detail, like how to build a system where it's important to integrate a new component into a super legacy system, and for this component to collect telemetry data, protect it, send it, and process it, there is a link, and we have a case study on our website about this. Another example, a more practical checkpoint about cryptography. Remember, I told you that it's important to consider the security of this device interaction protocol. Why? Because even if the protocol is encrypted, sometimes it can still be hijacked, sometimes the device can still be taken over. How? In this blog post, our cryptographers in 2022 had very interesting cases, with what we call gaming machines and controllers for gaming machines, where without breaking the cryptographic protocol through a replay attack, it was possible to simply send encrypted commands and the machine would turn and do what was needed. It's very interesting, if God forbid you are going to create your own communication protocol with a device, don't do it. Most likely they will, and most likely you will not take into account all these issues of communication protocols, the forward secrecy, backward secrecy, replay problems, and so on. If you're very interested, there's a link to a blog post. Next, what else? We also have a link on our website about agro drones, where very smart boards had the capability to process CABDA and ML model. Yes, there was a specialized module, a Google Coral board, which is capable of processing a model, and a specialized model was sent to the boards. The model is very efficient, and it was updated every few days. And the problem with this whole story was that the model is very sensitive. It's very important. Whoever controls the model, those devices are effective. And here is a whole case study about how we built a protection system around the model, because the model itself is just a dumb file. It cannot protect itself. And how, layer by layer, it was possible to build protection for this model And the last example here is precisely the problem of identification. Remember, I mentioned that the problem of device identification is not as simple as it seems. In collaboration with the Ministry of Defense, the Ministry of Digital Transformation and Aerial Reconnaissance, we have been developing the drone ID technology for over a year. It is already in use by some manufacturers to track both their own and foreign devices, ensuring trusted telemetry and confirming that the data and devices are indeed theirs. There are so many, I can't tell you, links to the Ministry of Defense website. For those interested, come and see. They're already. In short, it's a live system, it's in progress, and it's operational. And there are also manufacturers integrating into it to ensure friend or foe identification, to avoid attacks, and to reduce the number of friendly fire incidents. Well, cryptography is what drives it. That's it. I'm done. No, not quite done. Wait, that was everything, in short. Well, just a moment. So, I know that there is a collection for inverter generators at the conference. This is the main collection. But are you perhaps interested in robotics? And are you perhaps familiar with the NGO Aerorozvidka and their principle that robots, not humans, should be fighting? There is also a link for donations. This is specifically for robotics. So for those who have spare funds and are interested in killer robots, let's donate. Agro-drones and vacuum robots. Yes. Yes, did you take photos, right? Well, there will be slides. Closing remarks. Probably the idea I repeated most often in this presentation is that robotic and autonomous systems are significant. The security of such systems is extensive and multi-layered. We are not thinking about the security of a specific component, but rather the component, data flow. Another component, data flow between them, meaning multi-layered, truly large systems. Secondly, people. The more automation, the more things are written. And automated with scripts, the simpler it becomes. People only introduce errors. And these errors cost much more because of the work involved, because when a device fails, waiting for components from China again is very time-consuming and very expensive. And lastly, as architects, when we design security systems, it is our responsibility to consider all these complex cases, from mandatory reverse engineering to replay attacks, from issues that could introduce an evil twin device into our network, to challenges in trusting telemetry. That's all for now. Thank you very much.